Hello, Dr. Byrne. How are you?
Hi, how's it going?
Good. How are you?
Good.
Hello. Welcome to our webinar on High Rise. I'm Flora Zhu, a sophomore from Great Neck South High School, New York State. I'm a student volunteer for the Planet Plus AI program. I'll be your moderator today. Our speaker today is Dr. Shane Byrne. Dr. Byrne is professor at the University of Arizona. He is the investigator on the High Rise and Praxis cameras on Mars. He's also on the Dawn mission at Ceres. Dr. Byrne is the director of the Space Imagery Center, a NASA regional planetary image facility at the University of Arizona. Dr. Byrne got his PhD from Caltech in 2003. Today's topic is on high-rise images of the surfaces on Mars. This event is supported by the National Science Foundation and also by the Tennessee Space Grant Consortium at UT. And this webinar is live streaming now. Dr. Byrne, would you please share your full screen?
Yes, just a second.
All right, I'll give it to you.
Can you guys see the presentation okay?
Yes.
Okay, well then I'll get started. Please, anybody feel free to interrupt if there's any questions that come into the chat or so. I'd be happy to just take them in the middle of the presentation as well as at the end. Um, the topic today is exploring Mars one giant image at a time, and like the introduction said, I work on the HiRise camera, which is a camera that can take images of Mars at resolutions of about 25 or 30 centimeters per pixel. So that's about the size of a beach ball on Mars. So we can see things that are pretty small, and that's helped us really understand a lot more about how Mars works today. So I'll try and start by just talking a little bit about, why we study Mars and how it's both similar and different from the Earth. In a lot of ways, Mars is very similar to the Earth. It's a rocky planet, so much like Earth's continents, and it has about the same surface area as Earth's continents. The rocks are made of similar material to what you find on the Earth, although more similar to the rocks on the seafloor of the Earth than the continent. The planet itself has an obliquity, so that's how much it's tilted over compared to its orbit. That's quite similar to the Earth. So 25 degrees from Mars and 23 and a half for the Earth. And that gives Mars and the Earth more or less the same type of seasons that, with the same amount of darkness at the North Pole and the South Pole each year. And they both spin at about roughly the same rate. So Mars's day is about 24 hours and 37 minutes long, and the Earth, as you all know, is 24 hours. So there's lots lots of things that make them very similar. There's also a lot of things that make Mars very different and exotic compared to the Earth. So the atmosphere is very low pressure compared to the Earth, about the same as Earth's atmosphere at an altitude of 100,000 feet. So very thin atmosphere. Um, the composition of the gases are different, carbon dioxide versus nitrogen here on the Earth, and it's much colder. They both have a climate system that works in a similar kind of way, in that like sunlight comes through a transparent atmosphere, it heats up the surface, and so the atmosphere gets heated from below. So you see a lot of the same weather patterns on Mars as you do on the Earth, but also some differences in that it's cold enough for this carbon dioxide atmosphere to freeze out each year, and that leads to lots of interesting surface features that we can see some examples of later on. So geologists care about Mars because you can see all the same geologic processes on Mars as you can on the Earth, but you have a natural lab where you can study those processes with a different surface gravity and so on. Mars is also unique in the solar system in that it preserves terrains of all different ages. So early in the solar system, all the way through to current day, whereas Earth's surface is very young and we only really see the most recent part of solar system history. And then climate scientists also like Mars because it has got a lot similar that's similar to the Earth, but also it has these critical differences. So it allows us to test our understanding of how climate works in a situation that's close enough so that we can use the same models, but exotic enough that we're actually able to test those models. Okay. There's also lots of evidence for early water on Mars that has since evaporated away. So we'll mention that a little bit as well, because that's an interesting way in which the Martian climate has evolved that is of great concern to us today. Okay, the other reason to study Mars is that it's probably a link to a lot of terrestrial or extrasolar planets, terrestrial extrasolar planets that will be discovered in recent years. So here's a plot which is a little out of date now, showing all of the known extrasolar planets, their radius on the y-axis here, and their distance away from the central star on the x-axis. And a couple of examples from our own solar system, like Earth, Mars, and Jupiter, are in there. So most of the planets that have been discovered so far are bigger and closer to their stars. That makes detecting them easy. But pretty soon we're going to fill in this whole area. There's some brand new missions that are going to go up to detect extrasolar planets, and pretty soon we will know about thousands of planets around other stars that are Mars-like. So understanding Mars will help us understanding all these extrasolar planets too. Okay, so I'll give just a quick overview of Mars itself. So here's the topography of the planet. So this is showing you the height of the terrain, where the red areas are high and the blue areas are low here. You notice that lots of really big features, like this giant impact crater here. This is the Hellas Basin. Volcanoes here that are the largest volcanoes in the solar systems here, the red mountains with the white tops here. And then this big area here in the northern hemisphere where the terrain is really low, it's all blue. So you can see that that's a big basin, and it might have held an ocean at one point in Mars's distant past. So a lot of these features are very old and formed early in Mars's history, like these big shield volcanoes here, and the big volcanic bulge that they sit on top of are hundreds of millions of years old, or maybe billions of years old. This big canyon system, Valles Marineris, which is 10 times deeper than the Grand Canyon and much wider, is also quite old, like maybe billions of years old. So early in Mars's history, there's a lot going on. There's also lots of impact craters. You can see these small round circles here. These are all impact craters that have happened throughout Mars's history, ranging anywhere from like 4 billion years ago for this really big one, like for Hellas, to impact craters that we can see forming today. This one here is a special crater called Gale Crater. That's where one of the Mars rovers are, and I'll show a couple more examples of this later on. As I was saying earlier, we know a lot about water on Mars that has carved up the landscape in the ancient past. So if you look at landscapes that are very old, like billions of years old, you will see lots of dried up river systems like this. So here's water that ran along the surface and it emptied out here at the bottom. This is only really visible in the oldest parts of Mars, so all of this water activity is quite a long time ago, and the climate of Mars has changed a lot in the meantime. So Dr. Wang has been talking about her large language model and looking at alluvial fans, I'm sure to the rest of the group, and alluvial fans are one of the features that we see at the ends of these river systems, and there's a couple of examples of pictures later on in the talk where we'll see some of those. Okay, so how do we figure out then how this climate has changed on Mars, and how that might tell us about climate on terrestrial planets, including the Earth, and what the future might hold for Earth. So if we were studying this on the Earth, we would do it with the rock record, and we always look at climate records on the Earth in terms of the rocks that get deposited when these happen. So this is just a little picture of the Grand Canyon here in Arizona, just up the road from me. And the rocks at the top here are a limestone that tells us that 270 million years ago, Arizona looked like this. Right below that, it's a sandstone that tells us that 275 million years ago, so just a 5 million year difference, Arizona looked like the bottom picture. So there's a rich record here in the geology and in the types of rocks about what the climate has done. You have to try and ignore the camels, of course, in the bottom picture, or maybe substitute some dinosaurs in there in your mind's eye. No camels 275 million years ago. On Mars, we see similar things. So here's a crater that's, this picture was taken with a high-rise camera showing layers of rock inside what are probably old lake sediments. So this is material at the bottom of a lake, and it just keeps getting washed in by some of these rivers into these impact craters. So a lot of old craters on Mars have these stacks of layers inside them that tell us about the ancient climate on Mars, dating back billions of years. Okay, so this is kind of like a lot of information on this chart, but I just like to point out, when this big change on Mars happened and what was happening on the Earth at the same time. So we have down the bottom is the best place to start. This is the Earth timeline, and Earth's history is divided into these 4 eons: Hadean, Archean, Proterozoic, and Phanerozoic. And the earliest evidence we have for life is about 3.7 or 3.8 billion years ago, back in the Archean. Right before that, there was a period in solar system history called the Late Heavy Bombardment, where all of the inner planets got hit millions of times by asteroids and comets. There was a big shower of debris fell into the inner solar system. So we think anything on the surface basically got sterilized here by very high impact rates. Okay, so what's happening on Mars at the same time? Well, on Mars, we have a lot of evidence for water back in this period here called the Noachian. So this is back in the very beginning of solar system history. Then we have that late heavy bombardment. And as soon as that's over, life appears on the Earth, and Mars starts to undergo this big change into the dry and cold climate that we see today. So we think warm and wet early in the past, where we've got lots of clay forming in these layers, and then dry and cold later on, and we see lots of sulfates, a type of mineral forming in those layers. So many of these craters probably look something like this back in the Noachian. This is another one called Jezero crater that the Perseverance rover went to visit and is still there collecting samples. So we expect water in the craters, a river feeding that lake, and then an alluvial fan in some craters where the lake level is really low, or a delta in other craters like this one where the lake level is really high and all of the sediment is below the level of the water. Today, Jezero crater looks something like this. You can see the remains of the river here on the left, snaking around here and emptying into this crater. This is probably a river delta here, this fan-shaped object, and then the crater floor is on the right. So the Perseverance rover landed right around here where my mouse pointer is, and it's been driving up on top of this delta to try and take a look at this ancient lake deposit from the beginning of Mars's history. This is another delta on Mars that's in a different location on the planet, just to give you an idea of what some of these things look like. So it looks a little weird because a lot of the fine-grained material is gone, and you see lots of overlapping channels here that are basically just made up of like coarser grained stuff like gravel type material, so that that's less easy to blow away in the wind. This is Jezero crater again, but color-coded now for some of the compositional data that we have from another instrument on our MRO called XRISM, and just shows this purplish stuff, which is the water minerals called clays that are formed here in the lake. Okay, so a little bit of discussion then about the spacecraft we're using. So this is Mars Reconnaissance Orbiter. We've been in orbit around Mars for about 18 years or so, and HiRISE has taken about 89,000 images so far. In fact, I think it's 89,007 images as of this morning. So we just passed that milestone. So we take images of the surface that are really high resolution, but we also take a lot of pictures of the other missions at Mars, so landers on the surface or rovers that are moving around, and even the landing process itself. We've taken some pictures of these objects as they're descending towards the surface on parachutes. The way HiRISE works is something called a push broom imager. So really, a push broom imager takes an image that's only one line across. And as MRO flies across the surface, so let's say along this red arrow here, Mars Reconnaissance Orbiter flies along, and it takes many, many images that are each one line in size. And then we stack all those one line images together to make the full image. So this is different than a camera like in your cell phone, which we call a framing camera, because the framing camera just takes all the image lines at the same time. So you just get like a square area or a rectangle, and you image everything all simultaneously. In this case, you just take the first line of the image, and then the spacecraft moves a little bit in its orbit, and then we take the second line of the image. And this happens very quickly. We spend only milliseconds on each image line, but it's the spacecraft motion that sweeps across the surface and gives us the image data. The mirror for HiRISE is really large, so it's basically a big telescope. This is the size of the telescope up here in the top right. It's about 0.5 meter across, or about 20 inches. The field of view is about a degree or so. So it's not that different than if you look up and see the full moon in the sky. So that's about a degree across. But across that degree, we have about 20,000 pixels or so. So you get a very detailed look at that. So it's kind of like if you held your pinky out at arm's length, your fingernail on your pinky is about a degree or so. And you can imagine if you had a picture of your fingernail that's 20,000 pixels across, you'd be able to see lots of detail on your fingernail, and the same is true for Mars here. We can take some of this image in 3 different colors, and that allows us to make some of the color composites that we have as well. Okay, so one of the places that you can see the HiRISE data is on our website, which is uahirise.org, and I've got a link at the end of the talk for that as well. When you go to that website, you'll see a page that looks like this, and you can look at a HiRISE picture of the day, or you can go to this link here called Map, and then you can pan around the surface of Mars. All of these red footprints here, they're all individual HiRISE images. You can click on any one of them, and it will pop up this little dialog box, and then you can click on the link here, and it will go to a page just specific to that image. And on that page, you can look at the full resolution image, or smaller browse versions, or the black and white version, or the color version. So there's a bunch of different options. We have a red image that's the full width, the full degree across, and it looks something like what we have here on the left. The color one is only in the center strip, so just this little central part here. So that's narrower, only about 20% of the red image. And then there are merged images for the colors on top of the red here, and you can see what they look like together. These images here are map projected so that north is up, but these images over here, they're kind of like in their raw geometry. It's just the same way they come out of the camera. And Mars Reconnaissance Orbiter flies south to north, so south is at the top here at these images. That's a little bit of a distinction. Okay, but the color data, I just thought I'd mention, that what we're seeing here in these HiRISE images is not really natural color. If you were to look, natural color on Mars looks something like this if you were just looking with your eyes. So the contrast would be low, and the differences between different types of color would be pretty small. You wouldn't be able to see a very colorful scene. The images that we show you look something more like this. So this is the same scene. So this is where we've exaggerated the contrast. and we do some special processing to make the colors look as different as possible from each other. So the color differences are still real here and point towards different materials. But this is not what you would see if you were looking at it with your naked eye. So it's just something to be aware of as we take a look at some more of these pictures. So we see some areas on Mars that are extremely colorful, like here's one in a place called Lily Fossey. And it's got a good mix of things that I think is worth looking at. So this bluish material here that you can see arranged kind of in sand dune ripples. So this is rock that is pretty fresh, like it's fresh volcanic rock that hasn't been changed much and is pretty much the same as it came out of the volcano. And then there's this reddish stuff in the background, and these are rocks that have been around a long time, and they've been chemically altered into other things. So sometimes some of these clay minerals that we mentioned before, or sulfates. When you look at these pictures, you can see bluish type materials are more are younger and unaltered, and the reddish type stuff tend to be older and more changed compared to their original composition. And it's also just really pretty to look at. So with HiRISE, we also take pictures of some other things, miscellaneous things. So here's a picture we took of Phobos. This is one of Mars's moons. We did this, we had to flip the spacecraft upside down, so we were looking up instead of down. So some of these images are a little difficult to take, but also turn out very well. We can also look for changes because we're at Mars for a long time now. We've been in orbit around Mars since, well, let's see, I think 2006. So about 18 years now. And some of the changes we see are just really because HiRISE is so high resolution, and we can see things changing at a very small scale. So here, for example, these sand dunes all move at a couple of meters per year, but HiRISE pixels are 25 centimeters in size. So a sand dune might move like 10 HiRISE pixels each year. So after many years of doing this, we can see these sand dunes move pretty well. We also see avalanches on Mars. So here's a cliff near the North Pole, and there's an avalanche that's pouring down the slope here. And this particular location, these avalanches are very common. At some times of year, half of the images that we take contain these avalanches. So there's something very special going on in this one location that's really interesting. This is a picture, just blinking two pictures of the dune here. So this dark thing is a sand dune, and it's moving from right to left and just blinking back and forth between two pictures that are 3 years apart. You can see the front of this dune kind of moving over the surrounding terrain. So just having HiRISE be around for a long time allows us to look for changes like this. We've also imaged a lot of things on slopes that are moving downhill. So here's some things called recurring slope linii. So this is just a fancy term for saying that they're dark marks that recur every year and seem to pour down these hill slopes. We originally thought this might be evidence for liquid water on current day Mars because it looks a lot like water seeping downhill. Now we're a little bit less sure. We think maybe some dry processes that are related to so gas in the subsurface kind of destabilizing material and allowing just dry sand to run downhill might be the cause. But that's still something that people are discussing and arguing about. And then there's some features like this in the carbon dioxide ice cap. So this is dry ice on Mars, and kind of like dry ice on Earth, it's very volatile. So these pits in the ice, like this one here, expand at a couple of meters per year. So we can see that like happening pretty easily with HiRISE. We also see new impact craters form. So we have before and after pictures of impact craters. And with HiRISE, we can measure their sizes, and we get a better idea of how frequently we have impact craters forming, not just on Mars, but in the inner solar system in general. So there's a brand new impact crater that formed on Mars a couple of years ago. Okay. One other thing that I wanted to introduce about HiRISE is the fact that we can do stereo imaging. So we've got about 9,000 of these stereo pairs now. And we take stereo images more or less the same way that your eyes do. So we have an image taken with the left eye and an image taken from the right eye, and your brain can put that together almost in real time, about 10 times per second, to make a map of how far away things are. So it's a little bit harder with HiRISE. So we take one image and then we might take the second one a couple of months later. And it takes a couple of days of computers chugging on this to produce this terrain map of knowing what's high up and what's low down, what's closer to the spacecraft and what's further away. So what your brain can do in like 10 seconds or 10 times a second, it still takes several days for a computer to do here. Okay, sorry, I see a question in the chat. I didn't see this until now. So Stephen asks, are the alluvial fans on Mars similar to those on the Earth? Yes, they look very similar to those on the Earth. So this is one of the ways that we can recognize them as alluvial fans. They're typically like right up against a mountain front or the wall of an impact crater, and there's an obvious like river channel coming into it, and then you get this fan-shaped object that's moving away from there. I've got a couple of pictures of those later in the talk that we'll be able to see. But I think when you see the pictures, you'll just you'll know that they look almost just indistinguishable from something you'd see in a dry desert environment here on the Earth. Okay. So just as an aside, if you want to look at more of the HiRISE stereo data, there's a couple of ways you can do that. You can click on anaglyphs here in our website, and this will show you all the stereo pairs. And if you have the red-blue glasses, so they often look like kind of like this, they've got it's made of cardboard, and they've got the red over the left eye and the blue over the right eye. If you've got those glasses, then you will be able to see in 3 dimensions when you bring up these anaglyph images. Otherwise, you can click on this link called DTM. So this is Digital Terrain Model. And there's about 1,000 DTMs here on our website. And these are maps that are color-coded where, red is high and blue is low, much like the other stuff I showed a couple of slides ago. And you will be able to see then ideas or get an idea of what the topography on Mars looks like. If you click on any of those DTM pages here, then you'll get a little bit of a summary about where the observation is and so on. And all of these products that you can click on. So you can look at the colorized elevation. So this is color altimetry here. If you click on this, you'll see a product that looks something like that, where you've got an overview of the whole DTM. And then you can also click on things called ortho images. So these are just taking the images that made up the DTM and kind of warping them so that distortions from the terrain are removed. But those are also available on these DTM web pages. So this website that the team provides, uahirise.org, is a good resource for looking up the image data and where it is, or these stereo anaglyphs if you want to see the terrain in 3 dimensions, or these terrain models if you want to actually, do measurements about how tall features are or how deep any of the holes are, like that. There's plenty of other people who use HiRISE data. So here's a product from a guy called Sean Doran, where he made some perspective views of some mountains on Mars. And I included this one especially because you can see here these bands of material that are basically alluvial fans, because there's a channel upslope here, material pours down here and comes out. Now, we think these fans might be completely dry and not require liquid water at all, because the slopes are very, very steep at this location. But around a lot of the rest of Mars, the slopes are much lower, and fans there probably require some sort of liquid water to be able to wash the material down the channels and out onto the fan surface. You can also find a couple of flyover movies in the website that I just showed. So this is Mojave Crater, And I don't know how well this is coming out over Zoom, but it's a nice flyover movie. This is the crater rim here, and looking out of an airplane window as you're flying over the Southwest United States, it would look an awful lot like this, right? It's just kind of like desert type area with no vegetation, but otherwise the landscape doesn't look all that heavy. Okay, and there's another picture of Victoria crater here. This is a crater that the Mars exploration rovers went to back in the early 2000s. So that's one of the first 3D models that we made. And there's the rover itself on the edge. So one of the main things that HiRISE has done to be able to help Mars exploration is to help plan the rover traverses and the landing sites for a lot of these spacecraft that are touching down on the surface. So HiRISE does a lot of science work, of course, in its own right, but also helps exploration here. And our resolution is so high that we can see the tire marks or the tire tracks of this rover as it drives around on the surface here. So although you get like great in situ data from these rovers, like it takes a picture of one of these embayments here in Victoria crater, we can see views like this with HiRISE basically all over the surface of Mars instead of just one spot. So the rovers and the orbital science are very complementary to each other. We also support other missions like the InSight lander, for example. After it landed in 2018, it was like very high contrast because it landed and it blew away all the dust on the surface. So you get this big dark mark, and the lander itself is like very reflective and very bright. But then over the next few years, the dust in the Martian atmosphere just settles out over everything. So those surface markings are almost entirely gone now, and the lander is covered in dust as well. And in fact, it was the dust landing on the solar panels of the lander that really ended the mission for InSight because their power levels dropped to 0 and they could no longer charge their batteries. We can also take pictures of spacecraft as they approach Mars with HiRISE. So here's the Phoenix lander on its parachute descending down towards the surface. It looks like it's going into that crater, but actually the crater's in the background by a long way. So the Phoenix lander is going to land way down here, sort of in front of the crater somewhere. But we've, as well as choosing the landing sites and helping monitor the spacecraft on the surface and choosing the routes that the rovers take, we can help with the landing itself. And if anything goes wrong, then we'll have a better idea of what happened by taking these pictures. This is the Phoenix lander on the surface. So we have the lander up here, and there's a blow up of it on the right. And then there are other bits of hardware that have fallen off, like the parachute down here. You can see the parachute, it gets ejected in the landing process. This dark mark here is where the heat shield was jettisoned and the heat shield hit the surface. So, we can look at the aftermath of these landings and help figure out what happened. This is our view of Curiosity with the rover that's in Gale Crater as it descended down towards the surface. So Curiosity is still operating on Mars today. And this was an enormous parachute, the biggest supersonic parachute ever built at the time. And I think the Perseverance one might be even larger, but this parachute is maybe 20 or 30 meters across. So we got a really clear view of it. And then the parachute on the ground afterwards. We can see it blowing around in the wind actually now if we take pictures of this site. Now the parachute is in a slightly different place each time because the wind is blowing it around. Oh yes, and they even got a picture of that. So here's an animated GIF with the parachute kind of moving around a little bit due to the wind action. Okay, and then finally for the spacecraft images, we have the Perseverance rover, which descended in 2021. And Perseverance is going to study that delta in Jezero crater. And Jezero crater probably had that lake in it. So hopefully Perseverance is going to turn up some evidence of what early Mars was like and the climate and how wet it was, and potentially maybe even astrobiology, and if anything was alive in that lake, then that will be detectable as well. Perseverance doesn't do much analysis of the samples, so it collects all these samples and then stores them. And then we hope that another spacecraft will go to Mars in the next decade or so to collect those samples and bring them back to the Earth. This is Perseverance on the ground, and again, as seen from HiRISE. So Perseverance is the size of a small car, so we can pick it up pretty clearly on the ground. And we can also look at some of these other rovers. So this is the Zhurong rover from the recent Chinese mission to Mars. So the lander is up here, and you can barely see this rover tracks of the route that the rover took to drive around. This is the lander, the blow up of it, and this is the rover here. You can see the tire tracks for this rover leading straight to it. Yeah, we didn't work with the Chinese Space Agency to help them plan their mission, but we at least were able to take pictures and put them out there, and hopefully they find it useful. We're also able to tell as well when their mission ended, because the rover moved from here down to here. You can see these sand dunes here, kind of show you the locations from image to image between March and September in 2022. But then after September 2022, it didn't move at all, and we kept coming back every couple of months to take a new picture, but it was still in the same place. So we kind of knew that their rover, the rover part of their mission at least, was over at that point. Okay, and oops, that's the same picture with fours inside, so stuff's accumulating. We use these HiRISE data as well to plan out the rover routes. So this became really useful for the Curiosity mission. So this is a picture of Curiosity from orbit here that HiRISE took. And after driving over rocky terrain, the wheels on the rover started to look something like this. So there's a lot of damage to them. So we were able to map out a route for them with HiRISE images that was going to be a little bit easier on their wheels and mean there'll be less damage occurring to the rover. As Curiosity was driving around, it's in Gale Crater, which is another one of these ancient lake beds. In fact, most large craters on Mars probably have some lake sediment in them that date back to this era billions of years ago when Mars was much wetter than it is today. But Curiosity discovered these types of rocks in Gale Crater, showing mudstone, which is just basically lake sediment here. And this plot, which is a kind of common NASA plot, just kind of tells you where we fit into the set of missions that have gone to Mars so far. So Mars Reconnaissance Orbiter is over here. We launched in 2005. There's been a couple of other orbiters since then, but the HiRISE camera is the best camera that is flown, outside of Earth's orbit. I'm sure the CIA and the NSA have better cameras that are staring straight down at us right now, but the best camera for other planets is still HiRISE. There's lots of international missions as well, like HOPE, and an upcoming mission from the Japanese Space Agency. The Chinese mission that we mentioned is here, and what's coming up in the future is this Mars sample return. So we have the Perseverance rover has collected a bunch of samples, and we hope to go pick those up later in the decade. Okay, so Jezero Crater then, just to go into a bit more detail about this. It's not quite an alluvial fan, it's a delta, which means it's like an alluvial fan, but forms underwater. And when it forms underwater, it turns out slightly differently than a regular alluvial fan, in that the regular alluvial fan has just flat sheets of material building it up, whereas the delta has flat sheets of material on the top and then like a sudden decrease at the front. So it has this steeper area at the front of the delta here where you suddenly go into much deeper water. So we think this dates back to the lake in Jezero Crater that's at least 3.5 billion years old. Perseverance, which is the robot that is going to investigate that. Looks a lot like the Curiosity rover. So these are the two rovers side by side. They're very similar, except Perseverance has better wheels, so we don't have to be as concerned about that for Curiosity. So this is the type of wheels compare that they have. The Perseverance ones are doing much better. Okay, and I'll just show a quick video of the landing sequence here of how we got Perseverance down onto the ground, because it's kind of cool to look at, and sort of helps you understand the orbital picture that we have from HiRISE and at what stage it comes in. So it takes about 9 months to cruise from Earth to Mars, and most of that cruise is just unpowered, so it's just on a ballistic trajectory. So here we are approaching Mars. The first thing Perseverance does is dump the solar panels and the other things that it doesn't need for entry anymore. And then it has to steer itself through the Martian atmosphere using these little thrusters to maintain the right angle as it goes through the atmosphere. And the heat shield takes most of the brunt of this, and it burns off and slows the spacecraft down quite a bit. So one thing about this mission is that they put cameras on all parts of the lander, so we'll be able to see the landing from the point of view of the lander in a moment. But just to see this cartoon ad, we deploy next a parachute. So this is the largest supersonic parachute ever built. And then as you're coming down on the parachute, you'll see the delta in the background here on the surface. But when we start coming down on the parachute, we're still going about 1,000 miles an hour, but that slows down pretty suddenly to, maybe a couple of tens of miles per hour. And then we drop off the parachute because we can't take the parachute all the way to the surface. And the first thing Perseverance does is steer suddenly to the side like that, so it doesn't get hit by the parachute coming down. And then it descends the rest of the way on these rockets. So landing on Mars is a complicated business. The atmosphere is thick enough that you burn up once you hit it, but it's not thick enough to stop you in time before you reach the surface. So you need this combination of heat shields and parachutes and rockets, and it's always been tricky to land on. So anyway, we descend to the surface, and then we detach from that descent stage, and it flies away and crashes somewhere, hopefully harmlessly. And then the robot is ready to go on the surface. So this turned out to be a much more kind of violent landing than we were banking for. So when we got down to the surface, those rockets were kicking up like huge amounts of dirt and bits of gravel, and we found all kinds of stuff on top of the rover afterwards. So that's a kind of a lesson learned for next time, maybe. This is the picture we took with HiRISE of that event. So it was on the parachute still, it hadn't detached yet, and using the rockets. And HiRISE on Mars Reconnaissance Orbiter is flying past at like several miles per second. The parachute is probably still going close to 1,000 miles an hour. So we're passing each other like at this incredible speed. And so MRO has to roll to the left and pull up, if you think about it in airplane terms. So we do this like steep climb and pull up to the left so that the field of view of the HiRISE camera sweeps over this at the exact same time as this like 1,000 mile an hour parachute is passing through the field of view. So it's all quite complicated, and a tribute to people at Lockheed Martin who did all the orbital calculations for how to actually pull this off. And we got the image at the end of the day. There's another video I just thought I'd show because it's kind of cool, and it shows, from the point of view of the lander itself, what happens. So cameras on all parts of this. So here's the camera that's pointing back up, showing the deployment of the parachute as it's landing on Mars. And there's actually a coded message hidden in these red and white markings if you want to try and figure it out later. So that's something that you can try on your own time. There's the heat shield being jettisoned, and so these cameras looking straight down now. And the surface is still pretty far away, so I'm just going to skip forward a bit to when we get closer to the surface. But you can see the edge of the delta here already. And get forward to this because the rest of the landing, it takes a long time to come down on the parachute. And now we're getting close to the surface. So at this point, it's on the rockets now instead of on the parachute. And we should see it get close to the surface, and then those rockets are going to start kicking up a lot of the dirt that's on the surface and a lot of the gravel here. So here we go, coming down, and then these are the cameras that are pointing straight up again are going to show it being winched down off this sky crane. So we've got cameras on all angles. This is probably why it costs so much. But we have a camera pointing straight down from the sky crane to the rover down here in the bottom left, camera pointing straight back up. And this is where, you know, you can see chunks of gravel and dirt flying around everywhere on these images. And the lander got completely covered, but it made it to the surface safely. And of course, everybody is overjoyed at that. All right. And then finally, you know, HiRISE circles around 2 hours later and gets a picture of the lander safely on the ground. So this is our first view of Perseverance actually on the surface. So we landed right here where the yellow circle is, and one of the closest parts of the delta that's left. A lot of this has been eroded away over time, but one of the closest part is right here, this little mesa. And you can see what that looks like from the ground from Perseverance. So you can see the layers in the rock here. So there's some straight and then there's some tilted like that. So the way these deltas work is like it looks like an alluvial fan up here where it's above the water. But when you get into the water, then this takes a steep turn downwards. So you see these things, these steep beds that are called foreset beds. And you see the shallow beds or the flattish beds that are up here called the top sets. And that's what you're seeing over here. You're seeing the top set beds here and the foreset beds here. So at some point, the lake level was this deep, and that shows you, you know, where the water level was at some point in time. So different parts of the delta formed at different periods, so the lake level is probably going up and down a bit, but at this one time, then at least you have a marker here to show how deep it was. So we've been collecting samples since the landing. This is a little bit out of date, but just meant to kind of give you an idea that Perseverance is drilling samples all the way along its traverse and picking up different types of rocks. It also does some weather monitoring on Mars here. So we see lots of dust devils flowing by. So this is obviously very different from the nice lake that used to be there billions of years ago. It's not exactly the garden spot anymore, but still very interesting. And these dust devils are kind of cool just to watch them swing by. This is where the rover was yesterday when I pulled this off the internet. So we landed down here. And we drove around this area for a little bit, but then came over to the delta. We're driving up on top of the delta now. So this top part, more like the alluvial fan, right? So the rover is actually like on an alluvial fan right now. And then right now we're about to come off the alluvial fan and start driving up the river valley itself at the top here. And we've been on Mars for well over 1,000 Martian days. So one sol is a day on Mars. Okay, so you can follow like Perseverance and get an idea of what it's up to at any given moment by checking out any of these websites. But if you search for Mars rover or Mars Perseverance rover, it'll almost certainly pop back up as well. The website that I wanted to mention is also is our own UAHiRISE.org. So this is the website that I showed you how to where to find different images and different terrain models and so on if you're interested in that later. So I'll leave the URL up there, the UAHiRISE.org, in case anyone wants to note that down. I know there's a couple of other questions in the chat here. I can try and answer those. Sorry, I haven't been keeping up with the chat here. So first question was, does HiRISE make videos of Mars? A little bit, in that we only take still images, but we take sometimes many still images of the same place, and then we can put it together into a movie. So we saw a little bit of that with the dunes moving. That was only 2 different frames, but there's some areas on Mars where we've been taking lots of pictures, and you can see maybe a movie that's 10 or 15 frames long. So it's not like a movie in that the way you would think of it, but there are like time series of images that you can use to see how things move around. Okay, and then another question asks is are there earthquakes on Mars? So yes, this that InSight lander that we saw getting covered up in dust, its main function was to measure earthquakes on Mars. So it took a seismometer to Mars and it measured lots and lots of earthquakes. Some of those come from rock falls, and so a bunch of rock falls off crater walls, say, and that creates a lot of vibrations. Some of them come from new impact craters that are forming. So you get an impact, and we actually discovered some really big impact craters that had happened on Mars because we saw the seismic or the vibrations at the lander first, and then we were able to figure out where to go look with the cameras for that new crater from that. And then there are other types of earthquakes that we don't know what causes them, but we think that maybe it's something like the Earth where there's like tectonic faults that move and they still produce some earthquakes. Okay, a question from Lou: what optical sensors are on HiRISE? So HiRISE has a type of detector called a CCD. So this is what might have been in your cell phone maybe 10 years ago. Most cell phones now use a technology called CMOS. But a CCD is an older type of imaging detector and still more common in astronomy probably than CMOS. I think future cameras to Mars will use CMOS detectors instead of the CCD ones, but essentially they're very similar in that they're semiconductors that are light sensitive, and when photons of light come in and they hit like this pixel on the detector, then it creates an electric charge. And so we can measure the electric charges on these pixels to figure out how much light hits each pixel, and then we can recreate these images here. To make the color images, we do that with a red filter and a blue filter and a near infrared filter. And then we take those three separate images and stack them together into a regular red, green, blue image that you see. Okay, and then what optical sensors are on the rovers? So they're very similar to what HiRISE uses, except HiRISE has this enormous telescope in front of the sensor because Mars is very far away. We're 200 miles above the surface of Mars, and the rover is usually just like right next to what it's imaging. So the rover cameras are really small, and HiRISE is really large, but the sensors are very similar, and they use the same approach for making color images. They take lots of images with filters and different bands, and then they stack all those images together later to make a color image. Okay, and I noticed a Q&A here, it's a bit separate. Oh, okay, yeah, it's the same question. Okay, well, that's about all that I had today to show you, but I'm happy to take any questions now, and I know we're coming up to the last couple of minutes before 2 p.m. So yeah, just let me know what you're curious in learning about.
Dr. Byrne, I have a question. So are there earthquakes on Mars?
Yeah, so we had that InSight mission that I was just talking about, measuring earthquakes, and found quite a lot of them from impact craters and tectonic faults, and also from rock falls causing earthquakes.
Okay, thank you.
Yeah.
Dr. Byrne, thank you for your presentation on HiRISE, and thank you all for joining us today. Our next webinar will be on butterfly craters in the solar system this coming Wednesday, and I hope to see you again. Bye.
Yeah. Thank you, everybody.